Hey guys, it's Mr. Blake here. Sorry about this. I thought I was going to be here today, but we ended up having a big meeting at the district. So I want to just wrap up the last few concepts they're kind of outliers, but they're actually really important if you're into training or if the field you want to go in is maybe exercise science related. It's actually pretty interesting stuff. And then tomorrow when we come back in class, we'll talk a little bit more about some examples of these. But there's a lot of little new terms that you need to be aware of. So I'd like you to take notes. There's no formal note packet for this. So just make sure that you guys have a sheet of paper out. I'm going to do my best to get this up on the website, probably not tonight, but by tomorrow. In terms of the PowerPoint completed, so you guys can, if you miss something in the notes, you can go back and get it. But just a couple of ideas. We left off talking about how to increase the force of a muscle contraction. We said one way to do it is to increase the frequency. That is the electrical signals from your brain or your spinal cord going to those motor neurons and making them more rapidly fire to the muscle fibers that you want, the motor unit that we want. And eventually we get things like summation, temporal or wave summation, where these impulses just build and build and build, and eventually you get a fused tetanus, where we are completely maxed out. Basically, all of the binding sites on actin are occupied. We have so much calcium that all of the actin binding sites in a given muscle fiber are being used. But that doesn't mean that the number of binding sites limits our strength as individuals. We obviously have very different levels of strength. One of the other things that's going to do it is something called motor unit recruitment or multiple motor unit summation. And this is going to probably play a larger role in terms of just how much force we exert. I gave you the example yesterday, sort of jokingly, about lifting a pen versus lifting a 45-pound kettlebell. Obviously, my body adjusts to the resistance of each of those appropriately, so I'm not throwing my anything that's lighter than 45 pounds. I'm not like throwing it all over the room. So just a few terms here. This idea of getting more and more motor units to become activated is called recruitment. All right, and the more we get, the the more force we can generate. We typically start with small muscle fibers. So we're talking, literally the fibers themselves are a little bit smaller. They have fewer myofibrils. There's less protein. We tend to start small. Your body is in the business of energy conservation. It's not going to go big if it doesn't have to. As the resistance increases, maybe you begin to pick something up and realize that suitcase is more full than you thought. Happens a lot to me when I have to take my wife's bag to the airport. It looks so small, it's going to fit in an overhead compartment, but it's almost unliftable by human standards. I'm not sure how she packs it, but it's quite dense. More and more motor units would have to be recruited. Right now, until that happens, as you begin to pick something up, let's say you're picking up something really, really light. At the beginning, even though we're firing, okay, even though the brain is telling something to lift, if there's no, if the stimulus isn't enough to trigger calcium to flood and the myosin to bind the actin, we call that a sub or under threshold stimuli. That means the stimulus wasn't enough to trigger the action potential on the muscle fiber. Once we get enough, once the current depolarizes the sarcolemma, we begin to see, and then of course the calcium floods out of the sarcoplasmic reticulum, we're going to see what's called the threshold stimulus. Okay, that means it's enough to make the muscle fiber itself contract. Finally, we're going to get something called maximal stimulus, which is basically the strongest amount of stimuli that we can generate, the most calcium, all the binding sites, and that's sort of our upper limit. All right. Again, the muscle fibers themselves will contract even more and more vigorously. The sarcomeres will contract on itself, but there is a limit, right? There's only so many binding sites that can be grabbed. It can only be pulled so far, and then we're going to hit a threshold. So the way that we do this is to not necessarily make the fibers that we've already contracted contract even farther. Like I said, there's a physical limit to how much a sarcomere can contract. It's to get more fibers, and that's the motor unit recruitment part. Um, Beyond that, once you get beyond that, there's no way that you can continue to increase the force of your contraction. So you better hope that you have more muscle fibers, or, and more likely, those fibers have more myofibrils in them, which again do the contracting. So I think this is a really cool picture here, if we're looking at it. So you can see sort of right here where it says stimulate a nerve. So again, this is for maybe your maybe it's like a reflex response, or it's coming from your brain or your spinal cord. Until it hits, a certain line, until we get to a certain point, like right here, it's in white here. Let me see if I can get this. Okay, until you get to that point right there, you're not going to have anything. So if you look at these guys, this one, okay, this one, even this one, those may be firing from your brain to your fiber, but it's not enough to cause anything to happen. So it isn't until you get to here. And then here's the maximal stimulus line right up here, right? But these are all causing it to fire, to fire, to fire, and it's contracting more and more and more calcium's being released. And then finally you get to these guys, and even though your body's saying go, 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 this is all waste. Okay, this is all, once you're maxed out, it doesn't matter. Okay? It is completely toast once you hit your maximal line. All right, so the next part, let's just scroll forward, is looking at the size principle. All right, so once we've maxed out, again, it's how the motor units recruit. So at first we're going to recruit larger muscle fibers, smaller muscle fibers, and then eventually you get these really large muscle fibers up here. Not every muscle fiber in your body is built the same. All right, so I know it's, you think, oh, a muscle cell is a muscle cell, right? But it's really not. People who exercise more, lift more weights, consume more protein, can actually build the diameter of their fibers to even greater extent. So they actually have more contractile units in there, and therefore they're capable of generating more force when they hit that maximum amount of stimulation. All right, so two types of contractions I want to get into. The first one is the one we're probably most familiar with. It's called isotonic contraction, and that is where the muscle changes in length. I kind of abbreviated and made a little crash course ed puzzle for you guys I want you to check out, and he talks about this. But this is the one where we pick something up and that something moves. All right, so this is a majority of our contractions that we deal with. This is where we're actually getting the thin filaments to slide. So the myosin is able to pull, the muscle itself shortens up, it pulls on the bone that it's inserted to. Okay, so there's two types. There's concentric contractions, and this is where, again, if I'm lifting something, the muscle is going to shorten and do a little bit of work. And then there's eccentric contractions, which are a little unusual in that the muscle is still generating force, but it is lengthening while it does that. And we'll talk a little bit more about eccentric contractions. They are brutal. If you've ever tried to lower yourself from a pull-up very, very slowly, or brought with your bench pressing, bringing down the weight as slow as possible, or walking or running downhill, those are all types of eccentric contractions. And they're actually capable of building a lot more muscle. They're a lot more taxing than you think. Running downhill is really, really rough on your muscles if you're not in shape. So a lot of people think when they go for runs that the smart money is to run the downhill and walk the uphill. You're probably better off going the other direction just for overall joint health and muscle soreness the following day. But this is it right here. So you can see what we have. You have essentially what do you got it right over here? All right, so we have this guy right here. Sorry, I can't get the pen to go. There you go. This weight, okay, right down there, right down there. If that's 3 kilograms, you have to be able to generate enough force, recruit enough fibers, make sure that the stimulation, the frequency of stimulation is enough to actually overcome the 3 kilograms per whatever mass that is there. So you can see it's actually on this side, right? It's quite a bit longer. You can see the fibers here. And then you look here, they're obviously shorter, right? They've been shortened up considerably. So this muscle was able to actually remove or continue on from it. All right. So sorry, let's go back. All right. So that's isotonic, and you can see the length. If you look on that bottom graph right there, the length is actually decreasing as a percentage. It's going from 100% of its length down to 70% of its length as the peak tension releases. So as the muscle contracts, the length of the muscle gets shorter, and that kind of makes sense, right? Eccentric contractions are really weird. They work the opposite way. And it says the muscle is actually creating tension while it's lengthening. So you're still, the actin and myosin are still engaged. You're still forming cross bridges, but the myosin is not able to pull. Okay, it's not able to actually pull the actin. Now it's still pulling against something. I'm sure you guys have tried to move something that couldn't be moved. So you're still generating force, but it's actually going the other way. And this can actually generate more force than a regular old-fashioned isotonic contraction, which is why bodybuilders and powerlifters really use eccentric workouts to their advantage, but they will absolutely toast your muscles. Again, you're having the cross bridges form between the myosin and the actin, but it's unable to, because of the way that the weight is moving, it's unable to actually shorten. So if you're taking like a bench press and you have it over, you're starting with it straight out over your head, and as you lower the bar to your chest, your pectoralis major is resisting that movement. It's pushing back. It's keeping gravity from just slamming the bar into you, right? But the muscle itself is lengthening while it does that. So there's less cardiovascular demand, but it will lead to hypertrophy, which is muscle growth, a thickening of the fibers. But man, it is really, really rough if you overdo it. And the other branch of contraction is called isometric, and iso meaning same, metric meaning length. So here the muscle doesn't shorten. This is when you try to move something you can't move, basically. Here's the picture of this guy trying to push a wall. Not going to happen, right? So you still create tension, but it can't shorten or lengthen. Okay, so the tension is basically not enough, even no matter how many fibers you recruit, no matter how much frequency you give, how much stimulation, you're not able to move this object. And they again generate force, but they're unable to actually move it. Okay, and that's because of the resistance that you put there. So this is isometric. It's same. All right. And there you go again. Now notice the weight down there is doubled, right? It went from 3 kilograms to 6 kilograms. So we're pulling on it, but it's just not enough. Again, it's still a workout, but this, this is like when you flex your bicep. I don't know if I can do it on the screen. I won't do it on the screen because I don't want that getting out there. But when you flex, if you just hold your arm up and flex without moving your forearm, without bringing your fist towards your shoulder, if you just flex right there, the muscle isn't changing in length, but it is generating tension. Okay, and you can do that. The way that you do that is actually to contract both muscles at the same time. It's kind of cheating. You're actually activating your triceps and your biceps simultaneously, which is why when people do it, their arms look bigger. It's because they're actually contracting both upper and lower portions. Little trick. And again, here, look at the amount of the resistance. The tension develops never exceeds the amount required to move that object. So the resting length remains the same. All right. Last couple of things, muscle tone. Muscle tone is something that's pretty much regulated by not really your frontal lobe, but by your brainstem or by your nervous system. A lot of it's spinal reflex. So it's things that keep our posture up. If you look at people with spinal injuries, oftentimes they have difficulty remaining upright, and that's depending on where the injury or disorder or the affected area is. It could present itself in different ways. But basically, this is something that's out of our conscious thought. We're not telling ourselves to keep our head up or to keep our posture up. This is something that is constantly firing. Now, the cool thing is it's firing not on the same motor units, that there's sort of this alternating pattern that your nervous system uses so that we're not wearing down the same motor units. Yes, the same whole muscle is being contracted, but because it doesn't require a great deal of effort, it's able to contract different motor units at different times and balance out the sort of workload that way. All right. Again, I just want to quickly review this idea of how do we get um, maximum results from a muscle contraction? How do we generate the maximum amount of force? First, again, it's depending on the number of cross bridges that attach, but really it comes down to how many muscle fibers are stimulated. So that's how many motor units get stimulated. And remember, it goes from the smallest motor units to the larger ones, small fibers to large fibers. Um, how large those fibers are in your particular body, how much protein you consumed, how much lifting you did as a kid. And you're all, by the way, anyone who's listening to this is still in that range. There's still hope for you. I'm past that point, but you can still increase the size of your muscles and be able to get that back in old age. How frequently the stimulation comes, the neural signals from your brain and your spinal cord to stimulate. And then, of course, the last one is how much muscle stretch is there. And so I want to quickly address that. I don't want to get too caught up in this in terms of the numbers, but just an idea, something you may have experienced in life. There's sort of a sweet spot when it comes to how stretched out the sarcomeres are. And it's this, it's between 80 and 120, between 80, excuse me, and 120% of resting length. So if your sarcomeres are already shortened because you're in the middle of a contraction, you're going to be limited in terms of how much more, because you're literally going to run out of room. The actin will get pulled to the middle and you can't contract anymore. So if you can create a little bit of stretch, just a little bit of stretch before that contraction, you're going to get a greater sort of like a greater bang for your buck. You're going to have more ability to pull with more force. This is why people, if you ever watch someone who's doing the high jump, how do they get into that jump? Or if you're going to go jump in a volleyball game or try to dunk a basketball, most people are not as efficient as they can be from a standstill, right? So being able to load and stretch some of those muscles by those leading steps as they accelerate, as they hit that last step, the muscle actually stretches before it contracts. So it's sort of like pulling back a rubber band and then releasing it. And that will allow it. Now, you can overdo it. I did that once in a basketball game. I kind of took too hard of a step before I went to go dunk a basketball at a spring league game in Fullerton College, and my leg pretty much locked out, and I fell down, and the ball went out of bounds. It was one of the more embarrassing things that's ever happened to me. But that can happen. So providing a little stretch, same thing like jumping off of a box before you come up to jump. You will actually jump higher. I did that in a kinesiology class in college. We tested our vertical leap from a standstill, and then basically free falling from like a 1.5 foot box, and then springing up. And it's funny thing is it doesn't feel like you're jumping higher, but when measured, you actually do by providing just a little bit of stretch. Right. This is something we talked about yesterday, and that is the different muscle fiber types. I don't want to get too carried away. There's some extra notes in here, guys. But I just want to review sort of what we talked about yesterday, this idea of fast and slow twitch muscle fibers. Again, it's basically what it comes down to is when we're talking about the speed of the contraction, how quickly ATP can speed up the cross-bridge attachment, right? So you have ATP that's required to get broken down by ATPases, and they're going to attach to the myosin and pull with the power stroke, and then you need another ATP to grab that to take the myosin head and then pull it off, and then break it down again with another enzyme, okay, hydrolyze it, and then reattach. The faster you can do that, the more ATPases that you have, okay, the faster your contraction will be. It's this: how fast can you bring the actin to the middle, right? If every power stroke is like grab, pull, release, grab, pull, release, that is a slow contraction. But if you're grab, pull, release, grab, pull, release, grab, pull, release, because your ATP is both one, available, and two, the enzymes that make it into the energetic form are available. That's the most important part. You're going to have a contraction a lot faster. So those would be your fast twitch fibers, the ones that have a greater percentage of those, more of those enzymes, and your slow twitch fibers will not. The other way that we classify it is by the metabolic pathways. All right, how do we make, and we already discussed this, but how do you make ATP in that fiber? Oxidative fibers, oxygen, there you go, oxidative, oxygen, right? use aerobic pathways, and that's a slow process. Okay, so it requires oxygen to be present, um, and it doesn't happen very quickly. Either you're required to have a lot of myoglobin, which will contain your oxygen source, and a lot of mitochondria, because that's where aerobic cellular respiration takes place. You need mitochondria. So the more mitochondria, the greater the blood supply, the more myoglobin you have. That's going to give you a greater endurance, even though you may be sacrificing the speed, not having as many of those ATPases. Glycolytic fibers, glycolytic refers to glycolysis, and glycolysis does not require oxygen. All right, so these fibers are ones you're not going to see as much myoglobin, and they don't need oxygen as much. They're going to be your fast twitch, and they're going to run out of energy because they can't create nearly as much ATP as the oxidative. They fatigue a lot more quickly. Right? So there's a total of 3 types. You have slow oxidative, fast oxidative, and fast glycolytic. So you notice the glycolytic ones, the ones that don't have anything in terms of their ability to significantly, they of course have mitochondria and they make a supply of ATP, but it's not, but it's pretty insignificant compared to the other two. The dark fibers, or the slow twitch fibers, are going to be much more sort of like flooded with mitochondria and myoglobin. All right. Most muscle fibers have, most muscles have a combo of these fibers. And so really, depending on the muscle that you're looking at, it's going to have a greater percentage of one or the other. So if you have a single motor unit, though, it's going to be either all one or all the other. All right. And a lot of it's genetics. Like I think I mentioned this in class already. There's just people who will never be an explosive jumper. And then there's people who are just born quick and explosive, with great vertical leaps and fast reflexes and great agility and cutting speed. And then there's other people that are just slow, but they may be able to run a marathon. It just really depends on what kind of athlete you are. My wife is a fantastic endurance athlete, but she's not explosive. I mean, she's okay, and she's really trained herself, but she is not. You can put me out of shape next to her, and I would jump higher, not just because I'm bigger, but I have more of that sort of genetics going for me. But if you said, hey, go run for an hour straight, I'm going to be, 10 minutes in, I'm unconscious on the side of the street, and she's barely broken a sweat. So it really does come down a lot to genetics, sort of unfortunately for a lot of us. We can, however, use exercise to adapt some of these things. For aerobic or endurance exercise, if you guys are into that, here's what it does. If you guys were to start a training program, okay, so your focus would be on those slow twitch muscle fibers. What's going to happen in a lot of those muscle groups in your legs, particularly your legs and your core, what you're going to see is an increase. This is how your body will respond: an increase in muscle capillaries. So you're going to have a better blood supply so that we can deliver oxygen faster. You're going to start, those cells will begin to produce more mitochondria, okay? And it's going to begin to make more myoglobin. So anyone can kind of get in shape here. Again, some people are genetically better suited for this, just because they have more of these fibers, more of the higher percentage of these particular fibers. But this is called getting in shape. If you want to go run a 5K and you've been a couch potato your whole life, this is how you start. These are the physical transformations that are going to happen in your body, but your body must respond to some sort of trauma, essentially, before it will make any of this, which means you're going to have to be huffing and puffing for a little while. And then, of course, you begin to feel more confident, get better. As you're able to run a longer distance, it's because of these things. All right. A lot of times, what happens is you see these glycolytic fibers, your fast twitch white muscle fibers, turn into fast oxidative fibers. All right, and so they're going to get even better at being able to resist fatigue. All right. Resistance exercises like weightlifting, like this kid just throwing around the iron there. What's he doing? He's just pressing 225. Typically results in larger muscles. So if that's what you're looking for, that's what you do. You lift weights. No one ever got ripped by running. So yeah, you may lose some fat, you may cover weight, but if you're talking about building muscle, you're actually going to be wanting to lift some weights. Now, here's the thing. You were born with the number of muscle fibers that you have right now. Okay? And you can go put on 30 pounds of muscle and you haven't added a single fiber. What you've done is you've taken the existing fibers and you've added protein to them. You've created more myofibrils. And that's how your body responds through little micro traumas. You're going to, your body, as little tears happen when you lift weights and you put it under stress and you create oxygen debt and all that stuff. Um, those muscle fibers will respond by synthesizing, if there's protein available, and you have to take it into your diet, right? If there's protein available, your DNA will code for making more of those proteins because it says, hey, this guy's really putting me through the ringer here, and I'm hurting here. I'm got some trauma. So what do the cells do? What do those muscle fibers do? They begin to synthesize more of those myofibrils, more myosin and more actin and more of the other support architecture in there. And that's called muscle hypertrophy. You're also going to get more mitochondria. You're going to get in better shape too. Again, the myofilament glycogen stores, you're going to have that there for quick, explosive bursts of power. We want glycogen present. And then, of course, the connective tissue. And then we'll get an increase there. Well, we're going to talk about this tomorrow. So, yeah, whatever. Cool.